right now we're in this venue Maker Nexus, and I really appreciate being in here. And in this Maker Nexus, there's a lot of like cool things around like woodworking, as you can see here. And this is in this location outside this building right now. So afterwards, if you want to explore, you can go outside and explore the areas. And there's also like 3D printing. And in this image, I came over last night and then I saw this, so I took a picture since it's really cool. So yeah. And now we'll transition to Liam to introduce this event.
Hi, I'm Liam. I'm one of the makers on duty here at Maker Nexus. We are a nonprofit maker space here in Sunnyvale. We have a whole bunch of classes, and we also work on a membership model. So you pay for membership, and then you can come in and use the space and any equipment you're certified to use, and you would take classes to become able to use the equipment independently, and then you can come in whenever and use it, as long as you're a member. We always have staff members here, usually available to help you with whatever your project might be. We have woodworking, metalworking, laser cutting, 3D printing, textiles, electronics. We have a variety of CNC machines. We really have any kind of equipment that you might need for any projects or activities, local kind of clubs and things that come. We have like the Silicon Valley Woodturners that come and host events here. If you want a tour, please feel free to talk to someone at the front desk and we can give you a tour. We just have to make sure it's like a guided tour so we don't have people wandering around the space unattended, just so we can make sure everything's nice and safe. We also do summer camps and winter camps. We do a variety of different youth programs. And then we also host workshops, which are like project-based courses. Anything from glassworking to textiles, woodworking, really anything we do here. Yeah, please feel free to come stop by and get a tour if you're interested. And check out our website, makernexus.org. Thank you.
Hello, my name is Greg Murkowski. I've been inviting data science speakers for the local ACM chapter since 2008. I'm going to be introducing tonight's talk, a little bit of background about San Francisco Bay Area ACM. So we're a local professional chapter of the ACM. So how many people is it their first time coming to an ACM chapter event? Well, welcome. Thank you. How did you find out about us? Search on Meetup or? Yeah. Okay. And say, okay, sounds good. Thanks. So we're a bit older than Meetup. We were founded in 1957, and we've been holding talks like this on like at least 10 times to 20 times a year since then. We started the data science group in 2006. So we're a nonprofit 501c3, tax deductible for donations. It's a $20 annual membership. We have upcoming talks on our Meetup site and our past 200 more recent talks on our YouTube channel. So we have quite a lot of talks there too. So look for sfbayacm.org. We like to have meetings on both general computing and data science. We also like to offer networking, job hiring announcements. We are happy to work with other societies, IEEE, and various other things. You can use chat in Zoom if you're remote. If you have questions that we could read to the speaker, that would be fine. Also, if there's job announcements. Does anybody have any job announcements or company want to announce their company's hiring, something related to computer science? I'll start from one side of the room to another. Raise your hand if you want to speak. Or if you want to announce any other upcoming events or conferences that are interesting might be interesting to other members here. Okay. So my company, PivotXY, is hiring a data scientist and a Python developer. So we're working on some fundamental financial analysis. So we're an early stage startup. So we'd be paying at equity at this stage. We're going to be seeking VC funding and doing VC presentation shortly. So talk to me about that afterwards. Yes.
When is the break?
I don't know. It was there when I showed up. Does anybody know?
Spring. Parts of it.
Okay. Yeah, it was for the hungry zombies that might show up. Okay, and then upcoming ACM events. There's a global encryption day. Maybe I'll turn it over to Ron. He can talk about global encryption and also introduce the speaker.
Great.
Thank you, Greg. Hello, everyone. My name is Ron Petty. I'm a volunteer with the ACM chapter here, also this year's current chair. And so this event, the Global Encryption Day, is our next event. We've partnered with the Internet Society to put this on. It will consist of an all-day training around encryption technology and an afternoon, evening series of thought leadership focused style talks, things like quantum encryption and other interesting talks. It'll be in San Francisco in the SoMa area. So please sign up. It is free to attend. And if you register once, just be sure to register 2 days in advance. That's required to get access to the in-person events. It'll also be hybrid, so you can attend remotely if you desire. Bill,
Where do you sign up?
where do you sign up? Well, our meetup site for the San Francisco Bay ACM, or the site for the Global Encryption Day event, which is gedsf.org. So, yes, sir.
I tried to sign up on the meetup today, but it couldn't let me sign up.
Okay, can we try again? Okay, we'll try and see what's going on. Okay.
Can you put up the date?
Yeah, it's all on the website. Yeah, it's not.
Yep, upcoming events are on the meetup site.
Okay. Okay. So for today, today's meeting, I'm very happy and proud to be working here with the Silicon Valley Young Scholars Program. And so one of the representatives, Claire, she was going to be talking about the AI Copilot Socio-emotional training system for autistic children. So I have a little description about her excellent background, and then we'll get into a little bit about the actual agenda for tonight. So Claire's a student at the Harker School, is a strong advocate for transforming research innovations into tangible solutions for real-world challenges. Claire exemplifies a commitment to driving positive change through her endeavors. One of Claire's notable projects involves a pioneering and groundbreaking system aimed at training socio-emotional skills in autistic children using computer vision, why we're here tonight. Her research yielded compelling results with participants from 15 cities of 4 countries. 3 out of the 4 participant subtypes demonstrated statistically significant improvement, a testament to her innovative approach and dedication to addressing pressing societal needs. In another remarkable venture, Claire and her partner innovated sustainable fashion by developing vegan leather from 100% biodegradable materials. Her effort earned her recognition, including the national 2nd place of engineering at the 2023 Thermo Fisher Scientific Junior Innovators Challenge, as well as being named the national top 30 finalists. Additionally, Claire was honored with the Most Promising Young Scientist Award, driven by her passion for knowledge sharing and collaboration. Claire is eager to engage with like-minded researchers and enthusiasts to amplify the impact of research innovations. And so as part of the Silicon Valley Young Scholars Program, a URL will be available in the presentation at some point for you to check that out as well. And so for tonight's talk, again, the topic is AI Copilot Socio-emotional Training System for Autistic Children. Claire designed the HarmonyVisage system, a neuroscience-based AI Copilot training system that tailors to autistic children's individual preferences or subgroups and unique facial features. The BlendShape analyzer offers real-time feedback on socio-emotional cues and reciprocal eye engagement, and explains emotions using 13 measurable facial features. 4 phases of experiments were conducted with a total of 46 participants. Each participant went through an 8-week training. 3 out of the 4 subgroups demonstrated statistically significant improvement. So with that, I'd like to thank Claire. We're looking forward to this.
If you want, here's like the QR code to my LinkedIn if you want to connect later after this, and I'll let you guys scan it. And after this presentation, I can probably move back onto the slide. So a little about me, like I was introduced, I've participated in the 2023 Thermo Fisher GIC competition and won 2nd place for engineering. And also I was reported as the women's founder on Wednesday. And then, so for more details, if you want, for the next summer's events, we have a vision craft workshop hosted in June. So I'll just play this video. It's also on the SV website, which I'll show you later. So here we'll have the Vision Craft workshop for the ACM Silicon Valley Young Scholars from June 7th to June 8th. And it would be hosted at 9 a.m. to 5 p.m. at the Marriott Hotel, which is around here locally. And then so I'll skip through a little more. Yeah, so it would be in Santa Clara, which is nearby here. And then about the event, we'll have the computer vision workshops. And like here, there'll be the 3D tessellations of faces. And in here, you can see that there's different facial features. Well, there's 52 total facial features. And then also we'll have the mental health digital twin. And in this mental health digital twin image, you can see that there's me and also my mental health digital twin sister, which is the replication of my face based on the video I created. And then we'll also have 3D models, and this will include the face tessellation. And this has 368 facial points onto our landmarks. And then from here, you can like map out the facial features and be able to have a unique data set. And we'll also have a hand drawing AI recognition, which is really cool since it would be like hand drawing guidance recognition with 16 different educational levels. And in this image, you can see like there's a bird drawn, and then it's definitely like a really cool way to evaluate the recognition. And there's also like a selfie is like all about me in this image. And yeah, so okay, make sure that you sign up for next year's Vision Craft. And then I'll show you the website right now. So it's svyoungscholars.org. And in here, you can see the upcoming events, which is the Vision Craft, and you can click on the details to sign up. Yes, so I'm introducing the team right now. I'm Claire, the co-founder of SV Young Scholars. And the second co-founder is William from the Emory University. He actually recently graduated last semester. And William is deeply committed to advancing scientific developments in educational equity. So he conducted research on rehabilitative interventions and investigated neural pathways of motor control as well as cardiovascular diseases. So some of his main achievements include having received the Best Paper Award in the 2022 IEEE Prognostics and Health Management Conference, and has presented at the 2021 International Student Congress of Biomedical Sciences. And he's dedicated to empowering diverse young minds through equitable access to medical sciences and real-world innovations. And now introduce the third co-founder, which is Raymond in Carnegie Mellon University right now. And he excels in blending creativity and problem solving, from using game theory to enhance soccer shooting strategies to co-authoring the book Algorithmic Thinking for Adventurous Minds, which was ranked #1 in the Amazon's new release in the algorithm category in April. And he published multiple research papers in the world-ranking journals, and his mission is to inspire young minds through the lens of computer science. And Raymond is also envisioning applying his passion in algorithmic thinking to involving quantitative finance field. And now introduce Charlie, which is the VP in San Francisco region, and she's in fact right here with you in the room. And then Charlie, also known as Charlie, enjoys math and also balances her time between academic work and also athletic activities, including sailing and also rowing. And she likes taking challenges head on, including teaching herself the basics of game development and also competing in heavy weather sailing regattas. And she's interested in engineering and CS. She is fascinated about how STEM influences her everyday life, such as math applications in sailing and also physics principles in rowing. And we'll introduce our fifth member, which is the president of Equity Learning, and his name is Michael from the Cherry Creek High School. So Michael is genuinely passionate about STEM fields and active in research with AI. He co-founded Equity Learning, a nonprofit organization dedicated to bringing STEM resources to underserved communities. And he gave a powerful TEDx talk on his past video on game addiction in 2023. And he has since committed to organizing annual TEDx events. So these are the SV Young Scholars community. And now I'll talk about our agenda, which is color-coded based on the headers, as you can see up here. So first we'll be talking about the biological neural network versus artificial neural network. And then secondly, we'll be talking about the neurodivergent ASD population. And third, I'll talk about my implementation of AI Copilot socio-emotional training system. So starting with the biological neural network and artificial neural network. And over here, it's like a brain diagram, also biological and also artificial neural networks. And first, we could see this video of the Hubel and also weasel cat experiments in the 1960s. And this was to visualize how the cat sees images. So what they did was that they connected the sensors to the cells where they receive information of the vision. And then also they linked it to a speaker so that when the cells are fired, the speakers also make a noise. So they know that it's activated. And in here, at the very beginning, when they flashed different like dots, like black and white dots across the screen, the speakers like didn't make any noises, which meant that the cells were not activated. And afterwards, when they were like frustrated with it, they one time accidentally slipped the glass, which revealed a thin line, as you can see over there, like a thin line off the glass. And then that's when the speaker fired off. And then that's when they know that the cells actually were activated. And what this was saying was that the cat recognized the line because the LGN cells were oriented in a way where a certain amount of LGN cells are fired, which means that the V1 cells are also fired, which they happen to connect the sensors to. So another diagram over here is that from the eyes, you can see from the bird's eye view, the retina, and then afterwards it connects to the LGN cells, which stands for lateral geniculate nucleus cells. And in here, there's on and off centers depending on the brightness or like contrast between the edges of the images you see. So for example, if you see the biological neural network up there, it's you see like the B is a darker background contrasting with the lighter background in the back. And then if you look at the LGN cells in here, it's a wider and a lighter like color text over a darker background. So it's around the same idea for the LGN cells where you can see on and off centers where like in this case, the positive would indicate that there's a brighter center text. And then afterwards, if a certain amount of lateral geniculate nucleus is fired off in a certain orientation, it then transfers to the primary visual cortex, which is also known as the V1 cell. And then this V1 cell has this field over here, as you can see. It's like darker on the outside and also positive in the middle. And then now the top ones, as you can see on the top half, those are the LGN cells, since the neurons they're non-oriented and also have circularly symmetric receptive fields. And then when some of them are like fired or activated, it then fires off the V1 cells, which is orientation selective receptive fields. And now we can do a quick exercise. So can I get 4 volunteers here who wants to be an LGN cell? Okay, yep, you can come up here then.
You need another volunteer.
Yeah. Can we have 3 more volunteers here? Okay. Can be an LGN.
Excellent.
Great. And then LGN. And then there'll be an LGN cell. Such, and can we have one V1 cell over here?
Come on, Carol.
Got this.
Where do I stand?
You can stand anywhere in this place. So for the LGN cells now, are you guys ready? Yep. So then you can line up any orientation you want.
Okay.
Like you can like move around and then line up. You can make it like higher, diagonal, lower, anywhere you want.
I see what you're saying.
Oh, preferably like a line.
Oh,
Yeah.
Oh, okay.
Okay.
Put yours up. Wait, so
You're a V1 cell right now. So
So I
your
can't-
task right now is to orientate this paper to line up with the V1 cell to line up with the LGN cells. So right now the positives are in the center, be connected to a line. You see it's like a diagonal line, right?
Oh, so I need to be this way.
Oh, diagonal.
Diagonal.
Yeah, good job. So
Okay.
yeah, this is like a really simplified version of how this concept works. So if like these
Oh, I
cells are
see.
activated,
Yes, okay.
like all of these cells are activated, then it'll activate this V1 cell. But then, for example, if 2 of these cells are activated, but the third one is not, then this cell will not be activated.
And now he's down, so I can't do, he's down, up, down, so I don't know how to even replicate that.
Yeah.
So all 3 of us,
Yeah.
all 3 of us,
Friends. Some friends go up.
all 3 of us have to be lit up for you to light up.
Yeah.
Yeah.
There's
exactly.
millions of cells. So yeah. So that's how the concept works. So thank you so much for volunteering. All right. And yeah, you see the key is the edge detection. So in here, you can see that these edges over here, like light edges and dark edges, and the contrast between light and dark are those edges in between. And this is what the receptive fields in the V1 cells react to. Okay, and that was the exercise over there. All right, so now moving on to the artificial neural network for computer vision. So these V1 cells are basically the filters in computer science. And these filters have different weights. In this scenario, it's 1 on the right, and then 0 middle, and then -1 or 1 on the left side, 0 in the middle, and then -1 on the right side. And then in this case, it's a vertical. It's for detecting vertical edges. As you can see, the numbers are aligned vertically. But then if it was like aligned horizontally, it would be for detecting horizontal edges. And then now let's put the filter over onto this grid over here to detect the edges. So in this case, you can see that there's a 10, which represents the brightness of it. So in this case, 10 will be really bright, and the 0, which is dark. And then you can, like with the human eye, you can see that there's an edge in between the 10 and 0. But then for computer science, we would have to like put the filter over the grid and then find out where the edge is. So take, for example, this filter over here. Let's put it onto this grid. So the red here would represent where the filter is, since the filter starts on the top left corner and then finishes on the bottom right corner. And then, so when we put it up to there, the red side, we would multiply by the filter's size. So everyone, what is 10 times 1? Yeah, 10 times 1 is 10. So you see the 10 would correspond, 10 times 1 would be 10. So the number you would remember is 10. And then if you look at the second row here, 10 times 1, and then 10 times 1 is also 10. And then 10 times 1 again is 10. So you add them together, and that would be 30. And now let's move on to the second column. So 10 times 0, that's 0, right? And then afterwards, you move on to the second row, 10 times 0, that's 0, and then 10 times 0 is 0. And you add that together, and that would be 0. And then you do that again with the 10, and then -1. So 10 times -1 is -10. You add the 3 -10 together, and that would be -30. So we add the 30, 0, and -30 together, it'd be 0, which is what the results would be in this case, 0. And then now let's like do it one more time for the green. So the rolling window in this case would be 1, since the grid rolls or the filter rolls one column over. And now let's do this again. So 10 times 1 it would be 10. And then you add the 3 10s together, and that would be 30. And if you do 10 times 0, that's 0. And then if you add 3 zeros together, that's still 0. And then finally, if you 0 times -1, that's 0. And you add the zeros again, it's 0. And then 30 plus 0 plus 0 is 30. So that's why the second number over here is 30. And after you finish with the putting the filter over like this grid, you'll eventually get this result. And over here, the 30s would represent the edge. So that's how the computer would like recognize that that's an edge. Yeah, so now talking about like the deep learning intuition, basically deep learning is kind of like a black box, so we don't actually know what goes on inside it. But then in the most simplified way, it's kind of like an intuition. So in the most simplified way, it's like if you have like different edges over here, and then use the filter, you overlay it, and then basically filter it, then you'll eventually get like some sort of like image that you could see in this example, where you can see like some like facial features, like a nose as an example, and afterwards you apply the filter over it again, and then eventually you'll like develop like a face. And then back then, machine learning, like before then, people had to like manually input weights for the filter. So instead of like having like a 1, 0, -1, they would have to manually put in a number that would work out. But then now we have machine learning, and the machine learning like figures out the number themselves, which is really cool, honestly, because now they like optimize it for the best number. And again, like machine learning is called machine learning because it learns by itself. And now we'll move on to the second part, which is the neurodivergent, which is the ASD population. So we all live on like a harmony or like a spectrum. Since we respect everybody's uniqueness, all of us have different uniqueness. The harmonious landscape is beautiful because all of you guys are here, okay? So now I'll show you a talent. So my uniqueness is that I can identify which fantasy you want. So can I get another volunteer over here? Yes. So I'll go right there, I'll close my eyes, and you point at one of the images you like, and you hold it there for 5 seconds. Okay, and then standing here, you can like go up to the picture and then point on it. You can touch it and then touch it. Okay, and then I just make sure that she actually points at the images, the one that's your favorite. Okay, so I'll close my eyes and then you can like go and point at one of the images, and I'll go figure out which one it is.
Okay, you turn around.
Yeah.
Before I do it. 1, 2, 3, 4, 5.
All right, I'll turn around again.
Claire, you need to be over there for them, for the audience to hear you.
Okay.
It's getting standing closer to
Yeah,
you.
let's stay closer. Okay. So I'm wondering which image it is. Is it this one?
Yep.
Oh yeah, that's a talent right here. Because I'm going to type which image that you want. Yeah. Oh, okay, it's fine. Yeah, so all of us have different unique talents. And my talent is being able to know which image that you selected. And now let's talk about like the ASD population, which ASD stands for Autism Spectrum Disorder. So 1 in 36 children in the US are affected by this disorder, ASD. And then COVID-19 further impacts the social-emotional skills of people. So since 2000, autism prevalence has increased at 317%, which is wild. Since right now it's 1 in 36 children are diagnosed with ASD. And then in the 2000s, it's around 150 people. And then now let's talk about, or let's show you an example of someone with ASD and a neurotypical child. So over here, if you see the neurotypical child is sitting on the left side and the neurodivergent individual is sitting on the right side. And some like traits you can like see is that some traits you can keep in mind is that that the neurotypical individual has eye contact and also sits still. And then I can contrast them a little. So these are 2 quick videos playing between a neurotypical and a neurodivergent individual. So now they'll be going through like some interview questions, and you can like now see their social communication skills and how a neurotypical individual, they would like look at the camera or look at the person interviewing them and answer the question directly at them. Whereas the neurodivergent individual, they like glance around or like they look by the side.
Electronics, huh? What kind of electronics?
Mostly phone.
Yeah. Do you use an iPhone?
iPhone 6.
Nice. What kind of apps do you have on it?
I have no idea.
Alistair, how old are you?
I'm 6.
You're 6? What's your favorite color?
Green.
Green?
Yes.
Can you look at me? What are some of your favorite things to do? You have favorite hobbies, things you like to do?
Yes.
For fun?
Yeah, so those are some examples of someone who has autism versus someone who does not. And now talking about the official definition of ASD, it's defined in the DSM-5, which if you want to read like more about this, the details, you can look into the DSM-5. But then the main and primary differentiator is that the people with autism have a little more trouble with social communication interactions. So for example, they have these like the first few examples in A represents the social communication and social interaction differences, where they have like abnormal social approaches and also may have like reduced interest of sharing like emotions and also initiating or responding to like social interactions. And they also may have deficits in nonverbal communicative behaviors. And then they also might have deficits in developing, maintaining, or understanding different relationships. And then for the second one now, they can also have restricted or repetitive patterns or behaviors, interests, or activities. And then some examples here are that they're stereotyped or repetitive motor movements. And then also they might have an insistence or sameness of inflexible adherence to routines. And then they may have like a repetition of like certain movements, and then also like hyper or hypo activities. And now let's talk about the neuroscience behind the challenge. And then at this moment, I'll like pass around the brain where you can see the amygdala. And then the amygdala right here is like an almond shaped. And here in the limbic system, and the amygdala is like responsible for emotion processing. So I'll pass around the brain if you want to like look into the inside of this. And I'll talk a bit more on the neuroscience behind the challenges. So I summarized three main neuroscience facts about this. The first one is the amygdala theory of autism, where they have the lack of motion interpretation. So scientists have discovered that when the people with or neurodivergent individuals make eye contact, the fMRI shows that their amygdala is like less activated, and the amygdala is like considered like the social brain, and meaning like they don't like really the amygdala doesn't really like activate when someone makes eye contact with them, so they don't necessarily know to like make eye contact with someone else, or that's like an important trait. And the second one is the mirror neuron system, which in people with autism, they don't really show the sign of acknowledgement. And typically, if like for neurotypical individuals, for example, like if I smile, then then everyone else like tends to smile. And then when like I yawn, people tend to yawn. And then so like in a way, it mirrors my emotions or like the facial features I show. And then with people and in neurodivergent individuals, for example, they don't usually mirror like the different responses we have. So like if I smile at someone, or like someone with ASD, they might not like smile back, or like they might start showing a different emotions. And then sometimes like if I yawn, they wouldn't really yawn. So they have like a separate type of like emotion than us. But then it's in a way like they don't really always know like what emotion to show, since they might know that they should show a certain emotion, but they don't like really know how to show the emotion. And then so that is like one of the neuroscience behind it. So the second one is the mirror neuron system. And for the third one, it's a relevance detector theory, where they don't always like know where they should focus on. For example, if we're making like, or like if we're conversing or talking in a conversation, like I would usually make eye contact with you. And then that's how neurotypicals would usually like interact with each other. And then for neurodivergent individuals, they may not always know to like make eye contact with someone. And in fact, like they might be fixated in another area because they don't like know, or like they don't actually like know this like social-emotional communication skill to have, where they have to make eye contact with someone else. And then so in my project, I created a salience map to tackle this. And now existing therapies do in fact exist, like the most popular one, which is ABA, applied behavior analysis. But then for ABA therapy, it can be quite costly, since a session can cost around $120 to $150. It can happen like several times a week. And then also in ABA therapy, from a study of 551 records, emotional like skills are the least improved, which is what I plan to like combat. And now existing technologies also exist for like facial motion models and also for eye tracking. But then for facial emotional models, they're usually trained for neurotypical individuals on like their faces they have, like the different emotions they have. It's usually trained for the neurotypical individuals. But then for like the neurodivergent individuals or people with ASD, it's not really common to have these different types of models. And then secondly, for eye tracking, there's different like devices that may be a little bit hard for like neurodivergent individuals to wear. And also eye tracking can be like subjective in some cases. So right now I have like two categories over here. First one is direct and the second is indirect. So for direct, it's more like subjective since it has like human observations where the eye contact can be occurred in like time estimate of like seconds, where someone would have like a stopwatch with them and they would track like how long you make eye contact for. And then the second one would be indirect, which is which can be like hard to wear for people with ASD. For example, there can be like a video camera which is like zoomed into their face and can be like a little uncomfortable for them. And they can also have like head mounted or camera on glasses, which the people with ASD would have to wear, and it can be a little bit like stimulating for them. And then there may also be like cameras mounted to your monitor, and also like different cameras mounted onto your desk, which can be costly in some cases. And now I'll talk about the mysterious smile of Mona Lisa and how it affects your vision. So you look directly into her face, and you may notice like some subtle details, especially like her smile, for example. But then if you like look into like the fine details of her face, her smile may like even like disappear, for example. But if you view her in your peripheral vision, then your vision might pick up some low spatial frequencies, which refers to the broad or general shapes of her face or like the soft features of an image. And then now it may look like she's like really smiling, and it's like the smile is more pronounced. And this may also be reflected since like the shadows on her eye is like more uplifting, that if you look in your peripheral vision, then that is what your eyes may respond to. And then just a zoom in image of her smile over here. And then now I'll talk to you about the third section, which is the AI Copilot, which is social-emotional training system that I developed. So now, like I talked before, existing models, they are more like tuned towards the neurotypical individuals rather than the neurodivergent individuals. And also AI models output like discrete emotions, typically 9 emotions. And as you can see here, these are like the 9 emotions that these models usually have. But then emotions are actually like on a spectrum, since someone can have like a mix of 2 or 3 different emotions together. And this is an example of on the image on the right. Those are some examples of different emotions that someone can show. And also existing facial emotion models are not trained for ASD. And specifically in here, I targeted like the asymmetry or side glancing that some individuals may have. Okay, so to improve the social emotional skills, I tailored the model to like the unique facial features of the individuals. So on the left side, you can see that there's an image of a neurodivergent individual with like a bit of asymmetry or side glancing, because if they look at the computer, they sometimes look with the side of their eye. And then versus like a neurotypical individual on the right side over there. So if you see like the data on the bottom, you can see that there's a little bit of like asymmetry, like differences between like the eyes, like left eye and right eye, and also looking up or looking down. But then on the neurotypical individual, they may have like more like symmetrical sides of their faces. But not saying like their facial features are not symmetric. It's just like when they look into the camera, it may be, the sensor may like detect that it's asymmetric. And I'll go through like my training system, the workflow of it. So first one is I first like recruited 54 participants for an 8-week training, where 46 of them finished to the 8 weeks of the training, which is pretty impressive. And then when I first like recruited them, I tested like which subtype they prefer, which in here I have 4 main subtypes. First one is geometric preferences, which is the children with ASD preferring like different geometric shapes, like triangles or squares or other shapes. And the second one is animal preferences, since I saw like some children like they prefer different animals like cats or like dogs, because one of them told me that when they look at an animal, they're not like overstimulated because like the subtle movements or like features of their face. But then when they look at like a human face, they may be overstimulated because there's like too many emotions like overwhelming them. And the third one is hyperlexia, which is those with ASD. and they like looking at like words, not necessarily like understanding the meaning behind the words, but like they just like looking at the words. Like I had a few participants, they enjoy like reading books because they like looking at the different words and like the lengths of the words rather than like actually internalizing the contents of the book. And then of course I have other subtypes, which I categorize in the others group. And then now moving on to the first innovation, I had the HarmonyVisage, ASD multimodality data sets, and this included the 3D tessellation of the faces of the ASD individuals. And then I also have the facial analysis model. And over there, I have 468 facial landmarks I have mapped on the face. And then there's like 6 on the eye, and then like 5 on the iris. And then I then have like my second innovation, which is the reciprocal eye engagement. And this is like a system where I train like the children on. And then how it works is that there's like 4 training levels. First is that like is a pretest where they have to look at an image for at least 0.5 seconds. And if they look at the image for 0.5 seconds, they can move on to the 8-week training sets. And then the first level would be looking at cartoon faces, since it's the least stimulating of them all. And then afterwards, if they look at the image for 3 seconds, they can move on to the second level, which would be looking at their cells, or like, they'll be looking at themselves. And then by looking at themselves, like second one is actually looking at a still image of an AI-generated like face. So then it's still image, so it's like a set emotion and it may not be simulating. And then the third level would be looking at themselves, where they're like more familiar with their own facial features. And then the fourth one would be looking at like someone else, like a different trainer or like a family member, where they'll be practicing their eye contact for 3 seconds or longer. And then so I also like motivate the trainee with subtle improvements that they have shown. For example, like if they look at a certain area for like less than 0.5 seconds, the computer would like still keep track of how long they look at the certain area for. Like they can look at a certain area for like 0.3 seconds, and then I can like report it to them like on a meeting we have. And then my third innovation is the mental health digital twin. So over here you can see that there's me and also my mental health digital twin sister. And this is like to practice a fun and also like engaging environments for the children with ASD. And then afterwards, for the digital twin production, originally I have like I put it onto like Blender where I have to map out each face, but then eventually I was able to use LiveLink, which you can have like a video of your face, and then after that I can like put it into a mental health digital twin model. And then afterwards I also have my fourth innovation, which is for emotion analysis. And over here it's to model the emotions that the trainer has. For example, if a trainer is like showing happy in a certain situation, then the individual with ASD would also have to like model the feeling of like being happy, so that this way they know like what emotion to show. And this is because like before I've seen some students when they sometimes like show like a different emotion that, or like from what we perceive as a different emotion. For example, like they may be crying, and then when they ask like, oh, why are you crying? They're like, I'm not crying, I'm being like happy right now. But then they may feel like a certain emotion, but not know how to like actually show it to someone else. And now here's the tessellation of the different facial features. And as you can see here, there's 52 different facial features you can have. And then in here would be like different eye blinks, and also like eye looking up, down. And there's also like different mouth areas and other areas too. So here's like an example of what it would look like overlaid on my face. And then this is what the 3D tessellation would look like. So now we could have a volunteer, Charlie. Could you come up on here? I'll take a picture and then I'll upload the image onto Google Colab, and you can be able to see your 3D tessellation. All right. So I'll take a picture. Okay, thank you so much. And then now I'll upload it onto Google Colab. So, okay. I can show you the process of how it works. So I first airdrop it onto my computer. And afterwards, I can duplicate it. And then, oh, I can actually export it as a PNG image. So this is Charlie over here. And then I'll export it as a PNG image. And if I go into here, and then I click onto files and I upload the image. So it's this over here, and then I can right click it and then rename it to get the file name. And then afterwards, okay, I'll zoom in over here. So I'll put it into here. And now we can run it. So first I'll install MediaPipe, which is a computer vision API. And then once that's run, I can run this, which is getting like the face. And then over here to create the tessellation. And then over here, you could see the results of what Charlie's face was portraying. So for like brow inner up, it'd be a little bit, and there's more of like eye squinting somehow. And then there's like mouth smiling and also like mouth corner going up from the left side and also right side. And if you want to refer to the image again, I can show it here. So here was the image. If this loads, yes, this is image, and this is like the different facial features it corresponds to, and the different like values it has on the bottom. And then over here, let me see if there's, okay, it should have the tessellation, and this is a tessellation of Charlie's face. So if you overlay it in a way, then it would show it as well. I'll see if we can download it, and then I'll see if we can overlay it to show it. So this is the image. Okay. Well, it doesn't have a transparent background, but then what it does is that if you overlay these two images together, it would like fit onto your face. So that's how the 3D tessellation works. And then I created this for like the children with ASD or the neurodivergent individuals. And I'm currently like uploading it to GitHub, which is I'm still in the process of, so I can publish it afterwards. And this can be like the data set for the neurodivergent individuals. And I also have an example over here of the pictures sent. So here's a little bit of the animation. And then it would also have like different faces. So then, yeah, you can watch the animation. And then this, I think one more image left. Oh, here. And then this is the 3D tessellation overlaid onto her face. Yeah, okay. And I'll talk a bit deeper into like my innovative methods. So there's 4 innovative methods in total, and each one addresses a certain issue. So first one, the current issue is that the existing models are trained on the neurotypical individuals' image data sets, like I said before. And then what I did was that I had I created a 3D tessellation with 368 different facial landmarks onto their faces and also 52 different facial features. And then over here, you can see again the image of on the left of someone who's neurodivergent, and then on the right, someone who is neurotypical, and then the different facial features that they correspond to. And the second one, to address the current issue of the general training or like a high sensory environment, which is hard to focus in, I proposed a solution of a personalized training for with a mental digital twin. So the child here, as you can see, it would go through the pre-training, which would be looking at like a blink image of like a blue box on the eye area. And then if they look at that area for 0.5 seconds, they can pass onto the level 1, or they can start the 8-week training cycle. So for level 1, it would be a cartoon face. And then for level 2, it'd be a still image. And then level 3 would be looking at themselves. And then level 4 is reciprocal, which is they look at either the family member or like a therapist or someone else. And then after level 3, they can also like test their emotions and also try like relating their emotions onto the certain scenario. And then I also had like different subtypes. To repeat again, I had geometric subtype, animal preference, hyperlexia, and also others. And I also had like 2 different metrics. The first one is the % of reciprocal eye engagement. So how I measured this is the number of time or the time that the individual looks at the trainee or trainer, and then the time that the trainer looks back at them. So this way I can measure the eye contact time. And the second metric is engaging with the trainer and also the digital twin facial emotions like happy, sad, and calm. And in the data side, I can show like the graph of the like overlay between the trainer's emotion versus the trainee's emotion. And then for the third, to address the current issue of the people with ASD tends to have like a little bit of a longer learning journey, I created subtle improvement and also like personalized benchmarks. So I found that like typically for trainings like ABA therapy or other popular trainings, they can take like several months or several years to complete. But then with this, I was able to complete a statistically significant result in around 8 weeks, 6 to 8 weeks. And then in this image, you can see specifically targeting the second image over here. It's this is the image of me, which is when the child goes to level 4, where they look at someone else's image or video. I can, on my end, I could see a salience map or where they look at. So over here, the green represents like the area they look at the longer, like the dwell time, which is over 0.5 seconds, and that's considered dwell time. And then you can see that they were looking in like, I guess like the middle of my eye and also a little bit on the edge area. And then I can also see on the third image, you can see the dwell time, which is 0.44 seconds. And then that means that they looked at a certain area for that amount of time. And then now on the really left side, you can see the quick scan path of eye engagement. And there's multiple like points and dots there, where each one represents around 0.03 seconds of the eye movement. So in this image, you can see that the child looked a lot more onto the top right side of the image, as indicated by like more data points on that area. And then also on the right side, I have another example for the eye tracking on the X and Y coordinates. So over here, the individual looked more into like the center of my face, which is where you would want to look when you're like talking to someone. So over there, they made more eye contact with me. As you see, like a lot of the points were like grouped together in the center. And then now talking about the second or like the fourth innovation I had to address like the current issue of the emotions and how they're like how motion learning is like not innate to them. They require like a detailed explanation how these emotions work. I decompose like the facial emotions to 13 selected features. So originally there were 54 different emotions you could have, and then 54 different facial features you could have, and I shortened them to 13 selected facial features. So this way it's a lot easier for the trainee to like look at and be able to reflect onto their performance. So these 13 selected facial features correspond to their eyebrows, their eyes, and also their mouths, since these are like the most indicative features they have. And then as you can see in the neurotypical population here, you can see like some of the different facial features they have for like smiling, and then the ASD population also I have like 2 images of the ASD population. And on the right side, you can see the different weights of the emotions or the facial features they're showing. So the bar graph would indicate like more is that they're showing a bit more of like that type of facial feature. And I'll go over the 4-phase verification of the system design. And I'll go through each of them more in detail. So first one is exploratory phase, where I verified the system workflow. So to verify this, I related to the amygdala dysfunction. And in here, the features included 4 levels training procedure, and also included the digital twin and also personalized subset content, and the feedback, which is the dwell time, and also the motion responses that they had, like being happy or sad, and other different emotions, and also the dwell time as in like if they looked at a certain area for 0.5 seconds or longer. And the positive outcomes of this was that the children were motivated by the subtle improvements, and they were also more efficient in like training emotions with the 13 facial features. So for example, if they're like supposed to be smiling, then I could tell them like, oh, your right mouth corner is supposed to go up a little more to for the system to detect that smiling. So in other words, like from other person's perspective, they would know that the children's actually smiling. And then the observations I had for this, or the challenges, were that the children tend to like miss the focus area since they didn't really know to focus on the eye area. And there's also inconsistent digital twin creation from low quality photos. So originally I had to create 7 different photos from 7 different angles of the face. And then a lot of the times the photos submitted, they would have like, they would be like a little blurry, or the children would like shift around into a different like angle. So it wasn't always like the most accurate. And then there was also difficulties with long videos, since originally the videos were like 30 seconds, which were a little too long for the attention span. And then also I had measured like dwell time, but didn't really measure the reciprocal, which is what I was aiming for. So in the images you can see on the right side, it's on the top or half of the images are the information sessions I had. And I hosted these over the Zoom meetings where I had like a bit of icebreakers, and also led the people with ASD to draw a little bit. So there's like one of the talents, as you can see right there, of like drawing different cities or different like roadmaps of the places they have. And then on the bottom side, you can see the actual training results and how the individual focuses more on like the top right side. And then this is the quick scan path of their like vision, where they like looked across the screen and just glanced across and focused more on the top right. And now after this, I moved on to phase 1, which is to verify the practicality of my model. And I related this to the relevance detector theory since I incorporated the salience map. So the enhanced features I had in here were that I guided the focus with the salience map. So in this image over here of the cat, as you can see here, I first showed these images to the children to show like where you should be looking at. Then afterwards, they followed along with like the example. So it definitely improved a lot, since in this training with someone to like look at my face, they actually like started looking more onto the center of my face rather than looking to the top right. So that's also indicated by the X and Y coordinate graph over there. And then I also had I have to optimize the digital twin creation. So in like the end of 2023, MetaHumans actually launched, and that helped a lot, since now I can actually record like a 5-second recording of someone looking from the left to the right and top and bottom, and I can upload that onto MetaHuman. And after that, I was able to create this digital twin immediately. And then I was also able to shorten the video to 10 seconds, which was around the attention span of people with autism. And then I also included the metric on percents of eye engagements, or the reciprocal eye engagements. And the positive outcome of this is that 60.87% reached statistically significant results or improvements on eye engagements, and also 63.04% reached statistically significant improvements on showing their motions. And then I also met some challenges, which included that the parent and child were constantly together in training, but the parent wasn't like always involved in the training. Instead, they were more there to like make sure the child like focused onto the screen. And also, I realized that the reciprocal occurred like much less than the dwell time, since like children were like fixating more on like a certain area of the screen rather than like eye contact. And then also a lot of the children were distracted by this blue light screens. So they tend to like become shifty, or like they run away from the computer. And then so I moved on to phase 2, which is to measure the effectiveness of the training. And this one, I incorporated the theory of mind, which is false belief specifically, and also the eagle eye vision, where children with ASD tend to see 60 cycles of flickers. And then in here, I have the enhanced features of theory of mind training, where I also co-created content with like the parents. And to explain the theory of mind training, there's a really famous example of the Sally and Anne case, and I can quickly explain it. So for Sally and Anne, the case goes that there's like 2 individuals called Sally and Anne, and one day like the both of them are together, and they have like a little piggy bank, and then Sally sees Anne put like a bit of like coins in the piggy bank, and afterwards Anne leaves. And now afterwards Anne comes back. Sally leaves at that time, and Anne puts. Or actually, okay, I'll just say the story. So, sorry. What happens is that the individual will look at a certain scenario of Sally and Anne. And then the story is that Sally and Anne are friends, and Sally puts coins in the piggy bank and then leaves. And then Anne takes the coins out of the piggy bank and then leaves. And then Sally comes back. And then the question goes to the children with ASD of, oh, does Sally think that there's coins inside the piggy bank? And typically for like typical person, they would say like, oh, they would think that the coins are still in there because when Sally came in, she saw the coins being put in and then she left and didn't see it being taken out. But then for a neurodivergent individual, they will say that the coins are not there anymore because they saw Anne taking the coins away. But then they didn't like know how to look through the perspective of Sally, who didn't actually know that the coins are being taken away. So that's like how the theory of mind works versus the false belief. And then I practiced that into the training. So as you can see in the image on the here, it's the storyline of Sally and Anne, but I placed it with Claire, which is my name. And then it's like I placed a coin and I put like a coin inside the piggy bank and replaced it with a bill. And then I also recommended blue light screen filters for the children, since I found that they had eagle eye vision, since those with ASD tend to see more flickers of lights. So the blue light can be like really distracting for them when they look at the screen. So then with like a blue light filter, they're able to like focus more into the screen. And I also co-created content with the parents. So over here, you can see on these two areas, it's a co-creation of the parents. And then specifically one of the parents like took out fruits and then put in fruits again, and then acted like different emotions for the children to follow. And that was really helpful for like for the neurodivergent individuals to react to like a certain scenario. And the positive outcome of this is that there's 71.74% improvement on the eye engagement, and also 67.39% improvement on the emotions. And then also there were more like passionate parents co-creating these scenarios. For example, the parent you can see on this slide. And then some of the observations I had were that the children, they prefer like games, since the training could be like a little boring or like tiring after time. And then so I wanted to like gamify the training. And then this way the children have like more self-motivation to start training their eye engagements. And now move on to phase 3, which is enhancing the motivation of these trainees. And I related this to the mirror neuron system, where the enhanced features are the digital twin mirroring practices, and it also incorporated game scores. So you can see on the right side, I have different game scores, like if they look at a certain area for 0.5 seconds or dwell time at my eye area, which is highlighted in the green box, then the score would go up by 1. And then this definitely helped the training of the individuals with ASD, because I found like a lot of the individuals, they were more motivated by like short-term goals or like short-term happiness than like long-term goals of like improving their eye contact. And then the positive outcome of this is that there's 73.91% improvement of eye engagement, and also 78.26% improvement of emotions with their digital twins, where they modeled their digital twin. So over here, you can see on the image on the bottom of the screen, it's a digital twin of one of the children, and then they would like show different emotions, and the children with ASD would like try and model that. And then you can see like the child with ASD would like try and model the emotions of his digital twin. So now we'll talk about the participation distribution. I'll talk about the geographic distribution, age and gender distribution, and the number of sessions like for participants, and also the preference for the subtype distribution. For geographic distribution, my research expanded to 4 different countries, which is Canada, the US, China, and also India, and then also reached 15 different cities. And then for age and gender distribution, in total I had like 46 participants, and all of them, I had predominantly more males than females, and around like 4 times more males than females, which would be like considered like average, because males are actually 4 times more likely to develop autism compared to females. And then I also have the number of participants per session, or per session for participants. So like the number of sessions that each participant tends to go to, and like the number of times they trained. And they also have their preference subtype distribution. And this is an example of like over time, how many participants were in each subtype. So I had geometric preference, animal preference, hyperlexia, and also others. And on the first week, I had 13 individuals in the geometric preference, and then 27 in the animal, 5 in the hyperlexia, and 9 in the others. And then at the end of the 8 weeks training cycle, I had 10 in the geometric preference, 23 in the animal subtype, and also 5 in the hyperlexia and 8 in the others. And then now I'll talk about the data collection and analysis. So for reciprocal eye engagement, my first metric was to measure the percent of reciprocal eye engagements, which is how long, or like the percent of how long someone like looks into someone's eyes for eye engagement. And then this measurement was based on a frequency of 30 hertz or 30 frames per second. And then I calculated this based on the number of frames, or in this case, number of seconds, like the trainee would gaze into someone's eyes, divided by like the number of times, like the or number of seconds or number of frames the trainer looks into the trainee's eyes. And then for the data collection, I had like the top left corner is 0, 0, and the bottom right corner is 1, 1. And then this is like some of the data I had for the reciprocal eye engagements. And then as you can see in this, on this half of the side, it's the trainee's eyes are marked in green. So then this way the trainee would know like where they're looking at. And then the trainers, or like whoever's image is in the background, in this case it's like my face, then I can like make different emotions, and then afterwards the trainees can try and follow their eyes onto like my eyes to have like reciprocal eye engagement. And then on this half of the side, I have like the gamified version, which I have different scores, and then there's a box highlighting where my eye region is at. And then the trainee would try and look at my eyes, and then they look at my eyes for a certain amount of time, in this case 0.5 seconds, the score go up by 1. So this way they're like more motivated, or like they'll be like more motivated to try and train their eyes. And then for a second data collection, I had the facial recognition or facial emotion responses. And then this was my second metric, which is the facial emotion response. And the way I did this was also 30 hertz. And then I calculated based on the trainee's top 3 emotions, matching with the trainer's like different emotions. And then the data collection I had were the emotions and the intensity I had. And this was from Hume AI. And then as you can see here in the data table, it has like the different timestamp in seconds, and also the top emotions that were shown, or different emotions that were shown. For example, there were calmness, interest, concentration, and amusement. And there are around like 52 to 54 different emotions to show. And over here in this image is the digital twin version. And then also the trainees looking into the digital twin. So in this case, the digital twin is like showing an emotion like happiness. And then the children with the ASD, or child with ASD, will try and model the happiness by like smiling. And then in this case, the digital twin would have an emotion of like frowning, or like feeling a little sad. And then the trainee would like try and model that emotion, which is also like shown over here. And then my third data collection and analysis is the digital twin as a training partner. And this is verified with like test and control. And so over here, you can see that there's my digital twin, and also an image or video of me and live link with a face mesh onto my face to try and model it. So based on the emotions I show, it would also show into my digital twin. And then over here on this data table, you could see the engagements with the digital twin from the different subtypes. So these are the 4 different subtypes. And then it would have like the different amount of people who have engagement, and versus like people who are not like as engaged with the digital twin. And then over here is like the Hume AI of the top 3 emotions it shows. And now I'll talk about the results. So I had 46 participants continue through the 8 weeks training cycle. And then first, let's talk about the reciprocal eye engagements. So 3 out of the 4 participant subtypes demonstrated a statistically significant improvement on the eye engagements. The p-values correspond to geometric subtype, animal subtype, hyperlexia, and others. And the p-values were 0.027, 0.001, 0.158, and 0.001 respectively. So as you can see, 3 of the 4 subtypes show statistically significant results, as indicated on this graph over here. And then also for the emotions, you can see that there are like examples of different emotions, and then emotions of the trainee overlaid on the emotions of the trainer. So over here you can see that the trainer, happy, is indicated by the lighter yellow color, and the trainee with the brown color is like it's marked with the emotion of confusion. So you can see like how often they were confused throughout the training and how often like the trainer was happy. And then for the second one is the week 4. So the first one, this one is actually for the first week of training, and the second one is for the 4th week of training, which is halfway through the training cycle. So the participant would show like concentration, also like happy, and as you can see, like it begins to start modeling the trainer's like emotions. And then by the end of the 8-week training cycle, you can see that both emotions, the top emotions were happiness, where the trainer's emotion is indicated by the lighter yellow, and then the trainee's emotions is indicated by the darker yellow color. And then you can see how the trainee's emotions are starting to actually like start like imitating the trainer's emotions. And I'll talk about the discussions and next step. So I developed the AI Copilot system, which is based on neuroscience. And also it's to motivate the trainees with subtle improvements and also explainable facial features, as well as mental health digital twin. And then among the 46 participants, 3 out of the 4 subgroups achieved statistically significant results. And also I built the first AI system for a unique multimodality data sets specific for ASD individuals, like the 3D tessellations, where I'll upload the data set to GitHub. And then afterwards, after the 4-phase verification, like from the parents' request, they asked me to like upload some of the videos onto YouTube, which I did over here. And then I uploaded some of the training videos over here. For example, the theory of mind video, which you can watch in the YouTube channel. And also I have like the results and some examples of training where the individual can upload these videos onto their training sites. And then I also retrieved like the age distribution of the individuals who watch the YouTube, where a lot of them were from 18 to 24 years old and also 25 to 34 years old. And then also the different places that the participants are from. And then for the next steps, I would also like to expand this to younger adults who face challenges in interview, since an interview is like eye engagements, like with the interviewer, is quite crucial since it's a part of your non-verbal cue. And then so I would like to like expand this research to those who want to like improve their eye engagements with the interviewer. And then I also like to expand this to broader topics or broader groups like ADHD and also individuals with alexithymia, which alexithymia is a struggle to identify and also describe facial expressions and features. So in this case, like I use like the facial emotion model to for those with alexithymia to try and train them to identify more of like the different types of emotions. And then in the category of population of autism, 50% are corresponding to alexithymia, and also like 5% of neurotypicals also have alexithymia. Yeah, so going back to the image or the pictures I drew, and then how I was able to like figure out which was the image, it was actually from the collaboration of one of our participants over here. So thank you so much to Miss Charlie for helping us with here. I was able to actually identify the image because of collaboration, because she was like leaning on one side of the elbow or the other. So I was actually able to know which image she was talking about. I didn't actually have that talent, but yeah, I do have the talent to draw though. So these are some of the references, and then afterwards we can go to we can walk around and have a tour of the Maker Nexus, which they have like woodworking and also 3D printing and metal textiles. So thank you so much, everyone. So if you have any questions, you can ask me right now. Yeah, do you have a question?
Yeah, so I'm very interested with this work. So are you saying that you are making an app that can compete as an alternative to ABA therapy to improve ASD?
It's not really an app, it's more of a website, and then it's like to help those with like ASD, but then it's like I'd say that ABA therapy is like the more official training for like all types on the spectrum. But then for me, it's like those with like milder symptoms, or those who have a little bit of foundation on social-emotional skills, but then they want to train more on like their eye contact engagements.
So that kind of game for those kids, right?
Yeah, it's kind of a way to like help them. Yes, what's the question?
And parents and people that respond to themselves the way that they support them.
Yes. Yeah.
I have two questions. One of them was your code, the Google Colab. I was just curious, did you use like a code package or did you write that from scratch?
So I referenced like code from like different sources and I was like put them together. But then I wanted to create like a 3D tessellation, which I was able to use with MediaPipe. No, it's not that easy. Yeah.
You had to do
Yeah.
that together and function for your purpose.
Yeah.
I'm always curious about that. I think we all have sometimes the tendency to want full control and do it from scratch, but then we have to leverage but you address that. So thank you. And then my second question is, what are your thoughts on the emotional? I think we were saying that your model didn't perform as well on the emotional side of things, and that you thought that was a general challenge in the field.
So for emotional side, it actually showed improvement of the ASD individuals. I can show a bit of the percentage here. So yeah, so over time, I kept like training the emotion model where I had like originally it was just like a picture image of like of someone's like emotion, and then the children with ASD would have to like model it. But over time, I had like digital twin, which I was able to implement into the training cycle, where the child will like look into the digital twin and try and model the emotions. Because like in this version of like this digital twin, it's like a more simplified version of like a human face, so it's like less stimulating for them. So like they were able to like improve their motion after the time, and then by the fourth level, they're able to like actually look at a human being, like at a real person, and then be able to train their emotions off of that. Yeah, what is your question? Oh yeah.
Question was there, did you look at the motion learning by age group? Like I'm making an analogy with learning languages. Kids under 10 seem to be much easier at learning different languages. Just because their brains are more plastic. I didn't think that would be an effect here.
Yeah, so my age group was varying from 6 to 13 years old. And then in here I chose like the specific type because that's when like they're able to like improve their training a little bit easier. So like from 6 to 13 years old, they're able to like develop these different sets, the skill sets a little easier than like those who are a bit older. So it was more efficient for them to go through the 8-week training cycle. Did I answer your question? Or
I was just asking if you broke it out by age.
Oh, I didn't break it out by age. I broke it out by like subtypes, which is like the different preferences, which I evaluated in the pre-evaluation. Yeah.
Two questions. One was, you showed some code on the screen. I assume that was code that you or someone had to write for this.
Yeah.
How much code have you written?
Oh yeah, there was actually quite a lot of code I had to write. I did write and scratch a few codes. So then I had code for like creating the 3D tessellation over there. And I also had code for creating, it's not on this computer, but I also had code on creating this gamified version on Python, which is, I use like a different app to create it. And then also I had code to, it's not really code, but that has also had like a bit to program for the digital twin area where I put it on LiveLink to create the video, and then I uploaded it onto MetaHuman, where I then adjusted like different facial features, and after that I was able to create this individual. Yeah.
So it seems like there's significant amount of code that wasn't impossible. You did it.
Yeah, it wasn't impossible.
The other question I have is, was there any adverse reaction by somebody who was trying this out? Or, react badly to it? Can you repeat the question?
So like some of the adversity or like some of the hardships like the participant had, that like they reacted negatively to this training. Most of them reacted pretty positively. I'd say like the ones that reacted like a bit more negatively, I tried to address that into like the next phases. So over here I had like the different like observation challenges where like the main one was that the children didn't really like look into the screen. They wanted to like run away a lot of the times. But it was like I kind of found out it's because like of the eagle eye vision where they were able to see like 60 cycles of flicker. So then with this, like it's really stimulating for them to look into the computer. So after that, I was able to like put in a blue light filter, which helped them significantly, and they're able to like sit down and like look at the screen for around like 9 seconds or so. So after that, they're able to train for like based on the 10-second videos. Yeah. Also, like originally I had like a 30-second video and they would like always run around. So then I found like a general time of 10 seconds when they start like going like standing up and then running away. So I cut the video at that time. Yeah.
So there were kind of two major parts here. One was kind of implementing these advanced technologies, and the other was this kind of system that the kids interacted with that used that advanced technology and try to get certain skills to develop from them. I was wondering when you were designing all of this, to what degree did you start out and say, this is what I want to aim for? It's a system that does this, and then go off and figure out what technologies you need, or versus like I discovered some niche technology like for finding facial meshes. So now I'm going to figure out what experiment or what I can do with it in terms of building this system. So I was wondering how you balance those two or how that worked out.
Yeah, so originally I wanted to like just help.
Question.
Okay, so it's like if I first wanted to help, I think like from this based on like my idea like of what I wanted to do, and then I go and find the models to help with it, or like if I found the models and I tried like incorporating that into the system. Is that the question?
Yeah, I tried to, because you know how to do this, you're going to find an application for it now.
Mm-hmm.
Yeah.
Yeah, so like from system to like application. So originally, I first wanted like to improve the eye engagement of the children, and then I also like found out like different types of libraries, and then also being able to like track their vision. And after that, I incorporated that system into my I guess training system. And then also for digital twin, I actually learned about that recently throughout my project. When I was like in the background phase, I learned about it and I was like, oh, that's a really cool technology to have. And it's also like a more simplified version of like a human face. So then I was able to incorporate that into my project, and then it actually like benefited them since they were like less stimulated by this image. So it was actually a combination of like both sides.
Okay. Was there any idea that you had I want to do this, but you couldn't figure out how to do it with the technology?
Yeah, so for the digital twin originally, I had to upload like 7 images, and then it would be like from different angles, like from the front, top, and bottom. And then the individuals with ASD, like they tend to be like really shifty, so the picture would sometimes like turn out as blurry or not very like clear in a way. And it was sometimes like hard and like hard to like process the images to create a picture in Blender. And also it was also like really time consuming, since I have to like adjust each like facial point to like a certain feature. And then it was like at December of like last year where it was like MediaPipe was launched. And then that's when it helped significantly for my project, where I was able to like, record a video and then be able to upload the video onto MediaPipe, and it automatically creates the human for me.
I guess I'm also wondering, did you have a mentor who was expert in these areas who was helping you through this project? Or
I didn't really have an exact mentor to help me throughout the entire project, but then I also reference to my like school teachers sometimes when like I come to them for like office hours, and I ask them for like a bit of feedback, and they also like help me with the feedback of like categorizing it into like certain subgroups. And that's when I was able to categorize into the 4 different subgroups like geometric preference, animal preference, hyperlexia, and others based on the popularity of the children.
How old are you?
I'm 15 years old.
Wow.
Thank you so much.
Yeah,
You're like.
super young. What made you want to focus on autism? Is it sibling, parents, or people you just know, or is just something you were concerned about?
Yeah, so the reason why,
Could you please repeat the question, every question?
okay, so my inspiration for, she asked like my inspiration for this project, like why did I want to do this project for autism? It's because I had a reading club where like one of the individual actually had autism, and sometimes they were like hard to like keep up with the, I guess like the reading, and then sometimes like she would show like different emotions, and then would have like a bit of like tantrums occasionally, where she would say like, oh, I wasn't having like tantrums, or I wasn't like feeling this emotion, like I was like feeling happy, and then because of that I wanted to like help them with it, and that's why I created this system. And also like know a few like autistic or like people with ASD, and then from that I was able to like know that they also needed improvements on like their eye engagement. So that's why I developed this with eye engagement and also emotion recognition. Wait, can you repeat the question?
Source code available.
Source code available.
It's not published on GitHub right now, but I can like try and publish it later on. I'm currently in the process of uploading the tessellations or the dataset onto GitHub. So after that, I may publish the source code.
Are you able to do a demo today of this?
Oh, it's not actually on this computer though, so sorry about that. But I do have the tessellation of the Colab, which I showed before. But yeah, if someone else wants to come up and like demonstrate the tessellation again, I can do that. But then I don't have like the code for the eye engagement parts.
Was there any other questions online, Bill?
That was the question
Oh.
online.
Oh, okay.
What age did you start coding at?
Well, when I start coding,
What age
oh,
for you?
so in lower school and elementary school, I experimented with Scratch, which is like the really fundamental part of the coding. And afterward, I did a bit of Python in 6th grade during quarantine, since I wanted to like pick up a new skill. And then I tried to transition to Java. And then after Java, I actually took the APCSA course in like my school, just last year. And afterwards, I'm like going back a little bit to like Python for these like different codes.
One more question.
Yeah.
How much did language models help you with this, like ChatGPT or similar ones?
So the question was like, how did language models help me with this project? So for language models, it was like the main use of language models for me was like debugging my code when I couldn't find like the bug. So I kind of like put in the code in ChatGPT and be like, oh, what did I like messed up on? Like what was like some syntax error I had? And then ChatGPT was actually pretty good at identifying like which part I had. Sometimes like I would miss a colon or something, and then it would pick it up. So I was able to, so it was like really efficient for me to like use that for debugging.
Okay, we'll stop questions for now,
Yeah.
maybe some later.
Sure. Okay.
Thank you. Leave it for a second. Thank you, Claire. That was incredible. Thanks to the Silicon Valley Young Scholars. This is great work. So just as a reminder, mentioned this at the beginning, Global Encryption Day free, has training with the certificate, and it also has thought leadership track. Please come to the city, come visit us. We will be there. That's on October 21st. It is a Monday. You can skip work and come to this. And then coming up in the summer, just as a reminder, a follow-on to this work will be a camp to help people learn how to use this technology and experience it for themselves, and hopefully expand upon it and actually take these skills out and use it in the world. So thank you for coming, and that's it.
Thank you.
Thank you very much.
That was great.